In this video, I'm going to be modeling the beta decay process, and I'm going to be doing that with an oxygen 18 isotope. So beta decay generally happens with smaller elements that are radioactive, so things with less than 82 protons. When they're radioactive, it's generally because they have too many neutrons and not enough protons. So you can recall that the strong nuclear force is what holds the neutrons and the protons together. It's a very strong binding force. But because of all those protons, you've got this electrostatic force trying to push it or repel, push the nucleus apart. And sometimes when there are just too many neutrons, it just separates the protons enough that that is able to sort of take over that electrostatic force, and the strong nuclear force just can't keep the nucleus together very tightly. And that means that that nucleus is going to decay. So our parent isotope in this case is oxygen 18. And remember, we call it a parent isotope because it is going to produce a daughter. It's going to become something else. So this parent isotope has 18 total particles in its nucleus. So it's got a mass of 18. 8 of them are protons. That's why it's oxygen. When it undergoes beta decay, one of these neutrons basically is going to shoot a piece out. And that piece that it shoots out of there is this really small, tiny chunk that carries a negative charge, which means that that neutron, if you remove negative charge from a neutron, it turns it into something positively charged. Now, that tiny little piece that shoots out of it, that's our beta particle. And if you remember, beta, or maybe you didn't know this, but beta, the Greek letter for beta is just a B, with kind of a long tail like that. And this beta particle that shoots out of there with its negative charge is approximately, so that's your type of radiation, right? So instead of spitting out alpha particles, it's spitting out beta particles. And that little piece is about 1/1840th the size of a neutron. So it's super tiny, that negative charge. And so if you recall, things that are that small with a negative charge are electrons. So that's just an electron. The symbol for a beta particle, well, electrons have zero mass comparatively to protons and neutrons. And they're the opposite of a proton in charge, so they're kind of a negative proton, if you will. And so that is the symbol for your beta particle. Now, let's go back over here and talk about what happened to that neutron. So that neutron spit out a negative piece and became positive, right? Because neutrons are neutral, you remove negative, they become positively charged. Well, it only spit out a tiny little piece, so what's left behind basically is a proton. So if we look at what happened to our oxygen over here, our oxygen 18, well, we didn't lose anything from the nucleus that was significant in size, right? I mean, 1/1840th the size of that neutron is hardly anything at all. So we still have the same mass, 18. But we gained a proton because a neutron changed into a proton. So now we have 9 protons. And of course, that's no longer oxygen because oxygen doesn't have 9 protons, fluorine does. So our parent isotope, which was oxygen 18, has now turned into a fluorine 18, which is our daughter isotope. So our daughter isotope, what our oxygen turned into was a fluorine 18. So if we were to draw or write the equation for this, because sometimes it's easier to write an equation than it is than to like draw pictures. So we started with oxygen with 18 total pieces in its nucleus, so a mass of 18, 8 of which were protons. Sorry, my black pen is kind of acting up here. I'm gonna redraw this so it's a little easier. So 18 oxygen, 8 of them were protons. And it underwent the process of beta decay. And it became, so when it decayed through beta decay, it spit out an electron. So remember this little symbol for a beta particle. So that's your beta particle. and it left behind a fluorine 18. But if you do so it left behind still 18 pieces in its nucleus, but one of those protons or one of those neutrons changed into a proton. So this is what it left behind. And if you do the math, just like we did on the alpha decay video, remember we had 18 total pieces in the nucleus, and we should still have 18 on the other side of this arrow. Well, electrons have 0 mass, so there should still be 18 particles in the nucleus. So those add up to 18, which it should. And then of course the bottom number, remember that was 8. That was 8 protons. So we should still have that same number on the other side. But remember, that electron has a -1 charge. So it doesn't mean we're going to have 8 protons on the other side. It just means that whatever these two numbers are, they should add up to 8. And last time I checked, 9 plus -1. So we have 9 and we're adding that to -1. That equals 8, just like that. So that is the beta decay of oxygen 18.